Okay, so I guess I made a boo-boo. Because after looking at your assignment, I think that I need to clear up a few things, and I might have briefly mentioned some of these topics in the past two videos, but I probably didn't stress on it enough, and I just want you to go into this assignment with a very clear vision of what you should be doing and what some of these terms mean. Not really mathematics here, but just the terminology that's associated with normality. And the first one that I want to talk about is monoprotic. Now, if you've taken a Chemistry 151 or 152 course, you have probably seen this term before, but some of you maybe haven't, or some of you did take it, and maybe, again, you just had a lousy instructor that didn't explain it the proper way, and you've never heard of this term monoprotic before. So, mono means one, and protic means hydrogen. So a monoprotic solution or a monoprotic compound means that it gives off one hydrogen in total, just one. Okay, this is very important in the world of normality, because in normality we're looking at hydrogens like this, right? How many hydrogens is it giving off? How many hydrogens can it take in? So monoprotic is given to acids, but monoprotic is also given to bases. So in the field of an acid, it gives off the hydrogen, and in the field of a base, it takes up one hydrogen. So either one of those can be used for that purpose. Don't get them confused. They mean the same thing. It's just what's happening to the hydrogens associated with that particular compound. Well, you can kind of imagine that diprotic would be something very similar, right? So di means two, protic means hydrogen. So if I have an acid, it's going to give off two hydrogens, and if I have a base, a diprotic base, it takes up two hydrogens in total. So this would be something like H2SO4. Monoprotic would be something like HCl. Monoprotic base would be something like NaOH, and a diprotic base would be something like CaOH2, right? So that's what we're after. That's what we're talking about here. We do have a term called polyprotic. Poly's not going to cut it, though, in normality. We have to know exactly how many that we have. Monoprotic, diprotic, triprotic, you get the picture. Polyprotic is never going to be used in normality, even though it's a definition that's out there, which means many. Poly means many, right? Well, we have to know how many in order to calculate normality. Many just ain't going to cut it. We need to know, is it 5, is it 6, is it 7, is it 8, what is it? Both in terms of acid and both in terms of base. We have to know, okay? So that's just a quick review of some of the terminology that you might see in the upcoming questions in the assignment, and I just didn't want you to throw off or get thrown off of the question and get a wrong answer, just basically due to the terminology issue that you might have. The next one is something called equivalent weight, and equivalent weight is very similar to formula weight, but it's a little bit different, all right? So to calculate equivalent weight, we are talking about the equivalence, which means pieces. So the equivalent weight of an acid, the equivalent weight of a base, we're talking about part of the formula weight for each one. That's all that it is. All right. So to calculate equivalent weight, this is what we do. We take the formula weight of the compound, and we divide it by the number of equivalents that we're looking for, right? So for HCl, I would take the formula weight of hydrochloric acid and I would divide it by 1, because HCl only has one proton that I'm interested in, okay? I do the same thing with NaOH. I would take the formula weight for NaOH, and then I would divide it by 1, because we basically have one OH group. That would be the equivalent weight. So in those cases, equivalent weight is equal to the formula weight. It's a 1-to-1, very similar to molarity and normality being equal. All right, well, in the diprotic versions, I would take the formula weight of H2SO4, and then I would divide it by 2, because there's 2 protons that are there. There's 2 equivalents. So it's half of the formula weight. That's the equivalent weight for sulfuric acid. Well, what's the equivalent weight for CaOH2? You do it similar. You take the formula weight of CaOH2 and then you divide it by 2, because there's 2 OH groups. And that is what we call the equivalent weight for that acid. If there's a 3, you divide by 3. If there's a 4, you divide by 4. You got it. Again, though, it doesn't have to be strictly acids and strictly bases. It can be anything that it wants to be. So I can bring in BaCl2, and I can say, what's the equivalent weight of chlorine in this? So I would take the formula weight of BaCl2, and I would divide it by 2 if we're trying to calculate the equivalent weight in terms of chlorine. And that's because there's 2 chlorines for every 1 molecule. If I wanted the equivalent weight for barium, I would take the formula weight and I would divide it by 1, because there's 1 barium that's involved. Okay, it's as simple as that. A lot of people like to use equivalent weights for a number of different reasons. One, they're just not comfortable with moles and they don't like to use moles. An equivalent weight is a way to get around the whole concept of moles and stoichiometry. So for those people that have never really mastered or felt comfortable with moles and molarity and stoichiometry and balanced equations, they love equivalent weights because it gets rid of all of that mess. Equivalent weight, though, honestly, is not really used in a laboratory anymore. You see a few lab experiments or a few people out there that are still doing things by equivalent weight because it's somewhat of an older method that was introduced. And what we found out is that equivalent weight just made people even more confused. So now we just kind of drop that a little bit and we don't play a focus on it, and we just strictly go to molarities and normalities and stoichiometry from here on out. And it seemed to kind of clear up some of these issues that some of our people were experiencing in a laboratory when they would get a job or in a chemistry course, and we just kind of dropped it because of that. But I think it's important to at least introduce it, not go into full-blown theory of it, but at least introduce it so you know that it's out there and you might be familiar with it when someone brings it up. So equivalent weight is just basically a part of the formula weight. That's all that it is. And you take the formula weight, divide by the number of that particular thing that you have in the compound, whether it's 1, whether it's 2, whether it's 3, whether it's 4, whether it's 18. Okay? So that is what we call equivalent weight. So now that I've kind of presented those terms, there's no examples, there's no math involved, it was just terminology. What do these questions ask for? What kind of definitions might be presented that you might not be aware of? And here are a couple of them that you might see in the upcoming assignment. So now I think you're ready to go and tackle the assignment. Prove me good. Let me feel good about myself, because if I see high scores on these assignments, then I know that you're listening to my videos and I know that you're taking notes. Good luck.